Everyone, welcome to the third webinar of the Preparing for the PAT course 2024. My name is Kat, I'm the Physics Access Officer at Oxford University, and my pronouns are she, her. I run most of our programs for secondary school students, just like you, including all of our stuff to support people interested in applying to study physics at Oxford. Today's session is being recorded and it will be made available to you tomorrow. Quick reminder of the housekeeping rules for those of you joining us on Zoom rather than YouTube. You will be able to use the Q&A for any questions that you would like to be addressed. I'll let you know when this is switched on and ready for you. You can also access the chat to share thoughts and say hello as you are at the moment, but please keep it polite and kind and do not share any personal details or information. Also, make sure if you do have any questions, those go into the Q&A rather than in the chat, just to make sure that they don't get lost. It's amazing to see that a few of you have got to visit CERN. I'm enjoying this aspect. In the meantime, let's get started. So before we jump in with our second problem-solving session, I want to give you a very quick introduction to the course and to the PAT itself. Remember that although I don't take questions in this section, we have a webinar scheduled in September just for PAT logistics and questions. I'll repeat this quick introduction each week for new joiners to the course, and when we have time, I'll answer questions at the end of webinar. First things first, the PAT is the physics admissions test at Oxford, and it must be sat by all candidates for physics, physics and philosophy, engineering, and materials science. Your result on the PAT forms part of the information which admissions tutors use to decide who to shortlist for interview. And in that process, we go down from about 1,700 applicants down to about 500 people who we invite for interview. To sit the PAT, you must register yourself as a candidate. Your school will not do this for you. I'll talk a little bit about that process in a sec. The PAT this year will be on screen and will be completely multiple choice. There will be 40 questions with a total of 100 marks. And we've worked hard to make sure that we can gain as much information as possible from this format. So the answers are not simply 1 mark or 0 marks. The syllabus is unchanged and the questions will be very similar in style to previous years. The online test includes a built-in on-screen calculator, which looks exactly like a regular calculator and works in just the same way. The Physics PAT Prep course, which we are currently on a call for, is run on behalf of all the subjects which require the PAT. So I, as Physics Access Officer, talk to the people in engineering and materials science, and we run the course. It's a set of 8 webinars along with problem sets and summer assignments, and we hope that we're able to provide you with all the information that you need to take the PAT, to help you prepare for the PAT, and be confident at going into interviews if you are lucky enough to be shortlisted. The timetable on screen at the moment is part of the timetable which is at the bottom of every PAT email, and it's always highlighted to show you where we are to help you follow your progress. In each session, I'll fill you in on any updates or news, especially as we get closer to any key dates. This is our second study focus webinar, and you can see us highlighted in yellow. So today we're going to be focusing on waves and optics, and I will release the problem set 2 after this session. All of the information about the course and all of the course materials are on the course materials page, which I also link to in every email. The page looks something like this. This is a screenshot taken last week. The introduction to physics problem solving at the top has general hints and tips about problem solving, lots of which our teacher Rachel Martin covered in the first problem solving webinar, but there's a lot more detail in there as well. And then underneath, there are all the links that you need. So each week, I'll put up the problems that were used, I'll put in the recording, and I'll put extra things in there. Please do not use the chat for questions. I will get there. Okay, don't make me turn the chat off. Also, the problems which we use tonight are available, but we update after every session so that you can find everything. Finally, just a quick reminder that all of the information that you need, that both you and your school need in fact, can be found at this page. And again, this link is in every single PAT email. It's the most up-to-date page. It's the one to check first for any information that you need. And it's also got a really useful FAQ page for you. Some key facts. All tests this year will be sat at a Pearson test centre. These venues are in almost every country around the world. And when you register, you'll be able to select a centre which is most convenient to you. This means that our process is the same for our international candidates as it is for our candidates in the UK. And it also means that if you happen to be on holiday, hopefully you will still be able to arrange access to a test centre. For some people, this will involve some travel, but hopefully not too much. The arrangement's a bit different to previous years, but it's the same as the setup for tests like the LNAT, the BMAT, and all of the Cambridge admissions tests this year. The test format, which I mentioned earlier, is a new one. It's not as big a change as it might initially feel. So the questions are going to be really similar. The syllabus is really similar. Sorry, the syllabus is completely unchanged. The questions are really similar. But even though might feel like a big change, we don't want anyone feeling anxious. So you can access a trial version of the test. The practice test has already been released and is available at that website. The PAT date will be the 28th of October, and registration for the PAT is between the 15th of August and the 4th of October. You can apply for access arrangements when you register for the PAT. That's my quick PAT introduction and update. I hope it was helpful. I may be able to take questions during it, but at the moment, I'm going to stop screen sharing and hand over to Rachel Martin for our second study focus session, where Rachel is going to be working on waves and optics with you. I'll go over into the background. I will share any problems that Rachel puts up on screen, and I'll switch on the Q&A specifically for any questions about the work that Rachel is doing. Rachel, lovely to see you again.
Hello, good evening, everyone. Hi, good evening, everyone. Great to be online again with you all. And we are looking at a slightly different problem-solving session today. So I will just share my screen. And hopefully you can all see that now. So just a reminder, during this session today, if you've got any questions for me or for Kat, put them in the Q&A only. We won't be answering any questions from the chat, so we can keep track of them. And then in the chat, at first, the first few questions are multiple choice. So I don't want you to send any answers at first in the everyone chat, just like you send them to hosts and panelists. At first.
Would you like me to switch off everyone chat so we don't have any mistakes?
Why not?
For
just
the first
for a little
couple?
bit, Kat.
Okay.
And when we get onto the longer problems, we can open that back up again.
Perfect. That's done. So at the moment, you are all able to message me and Rachel, but not the big chat. And as Rachel says, I'll switch that back on for you once we're talking about the long ones.
Fantastic. Thanks so much, Kat. And today's session, again, we're problem solving. We're practicing our problem solving because that's the key. Practice, practice, practice. That's why we're on these sessions every week at the moment, and you've got your tasks independently to do as well. And here we're focusing on what students really like to leave out of their physics life sometimes. I find my students really avoid this topic, and it's waves and optics. So just really looking at something specific on the syllabus, but that's why it's really important this summer to make sure you're really clear on what the syllabus involves, and then we're practicing a wide range of our physics skills, not just relying on one thing. Okay, so Kat's just posted in our chat the problems that we're using today, but you'll be able to stick with me for the most part with this PowerPoint. So that's probably the place to stay for now, but if you want to check anything, there is a link there from Kat. Okay, so stick with me in terms of answers for now. This is a good resource for practicing physics and nice multiple choice questions. We've got our next time questions that you can find online if you Google that. And I'll leave you to read through that question. And when you think you've got an answer, pop it in the chat for hosts and panelists. And if you're thinking it through, how would you think about drawing a ray diagram? Put that mirror there. How can you see both your head and your toes in the mirror? Lots of people saying E, and that is incorrect. Okay, so have a little think. I've ruled one of them out. Okay. And as a matter of fact, we have sort of had quite a few get there in the end. Okay, so lots of people are saying D, your full height, but I'd just like to remind you that you probably have stood in front of a mirror less than your full height and seen your whole outfit, including your shoes. So I'm going to rule out D as well. Okay, so what answer can we settle with? Helps if you draw a ray diagram, especially using this as an example. Okay, I'm going to show you the answer. Okay, and the answer is actually B, half your height. So we're really using the law of reflection here. And if you look down halfway down a plane mirror in front of you, you'll see your toes. And if you look at parts of the mirror below the halfway mark, you'll see the floor, but not yourself. And if you look straight ahead, you'll see your eyes. Distance from the mirror, if you were to sketch this out, distance from the mirror is actually not a factor. If you look at the ray diagram, the end part of that explanation for that mirror that is sat on the ground. So you've got to think about the two extremes of what you're trying to see. The very top of your head, your own eyes, and your toes. That's three extremes, I suppose I've said. You actually need a mirror that's half your height. So I'll be quiet for a moment to allow a bit more reading. And if you want another good explanation for that, physics classroom has quite a good explanation as well. So for example, a 6-foot tall person would need a 3-foot tall mirror to view their whole image, regardless of where they're standing. Okay, I'll put another question up. We're using the laws of reflection and refraction today. So here is a refraction question with a twist. Have a little read. There are 3 options, so you can tell me what you think your answer with is in the chat. Thanks, Kat, for sharing that link to Physics Classroom. Okay, had 2 answers, but no one's got the correct answer yet, apart from one person. Elliot, you are correct. Now they're all coming, it's hard to, no one else has got it correct yet. I think everyone should reread the question. Just because you've seen one like this before, it doesn't necessarily mean it's the same. Well done, Sam. I think you corrected yourself. It's hard to keep up, so sorry if I missed you. Yeah, a few people correcting themselves now. And I'm going to just point out that this time we're using a laser to aim at the fish. So we're using a laser as the spear. Maybe it's a bit misleading how the diagram is drawn in this question. Good, lots of you getting the hang of it. The correct answer is directly at. Okay, so we are thinking about refraction here. So the image, I think that's probably the misleading bit. The image is showing the person seeing the fish, but then this person wants to use a laser to aim at the fish. Okay, so the question is about the laser aiming at the fish. So because of refraction, and you're right, the light from the laser will travel slower in the water, but because it's a laser that's going to aim at the fish, Huey should aim directly at the fish that he sees, because Huey is seeing the fish by the refraction of light. And so he should therefore use the refraction of the laser. He has to compensate for the refraction of light. But if the sphere is a light beam, the light path is reversible and will go from A to B along the same path it takes from B to A. So always about reading the question carefully in these waves questions. So a big theme of what we're looking at today will be reflection and refraction. I'll move on from this for now, but that is a good resource in terms of some quick multiple choice questions that also come with thorough explanations. So we're thinking about problem solving, how to solve these problems effectively. Again, my standard advice, learn your formula for all the PAT topics. Okay, so for all the relevant PAT topics, you'll need to know your formula off by heart. There's no formula booklet. Double check the syllabus. Make sure you know your definitions and equations. We're going to use a lot of definitions today, a lot of equations. With waves and optics questions specifically, always draw your own ray diagrams. So have a piece of paper handy now, or a whiteboard if you're practicing for what you'll be using in the autumn, okay? But it is advisable to draw a quick sketch of a ray diagram, even if you're given one. So sometimes I'll have ray diagrams popping on my screen today, but try and get into the habit today of drawing your own version before I show mine, okay? Label your angles really clearly. And don't forget today to use simple geometry rules to calculate angles. So take it back to basics, take it back to the mathematical rules that you know. We are going to be using Snell's law and for refraction and total internal reflection rules. And remember that unless otherwise stated, always the refractive index of a vacuum is 1. And air, unless otherwise stated, we can usually assume is acting as a vacuum. So from the syllabus, which you can find online, I'm not going to leave that there for long, but we're going to be looking at reflection today, the angle of reflection. We're going to be looking at refraction, refractive index using Snell's law, which you can see displayed on the screen here. Okay, we're going to be using the ideas of prisms, optical fibers. Don't forget that's often in A-level. And total internal reflection, as well as the idea of the critical angle. I'll be using all of these ideas today, and we need a qualitative understanding of how interference and diffraction and standing waves can occur. So that will be involved in the problem solving side of our course. So again, another multiple choice will be giving answers in host and panelists chat at the moment, but have a little read of this question. I'll just turn my camera off while I grab a drink of water. Excellent, you're getting the hang of it. So loads of people sending in some correct answers. Oops, sorry, I'm pressing the wrong button. Okay. And remember to read the question really carefully. It's a beam of coloured light, for example, red. You might be thinking the dispersion of white light by a prism, but this is coloured, beam of coloured light, so one colour only. What happens to the light of the prism? It's not C because the light refracts. Okay, so it can't continue horizontally. We can immediately cross that one out. What's happening at the prism is the question. So we know that refraction will happen. Okay. And I can see loads of correct answers came into the chat, but just be careful because that light will slow down. And one thing to always construct in a refraction question. Okay, so seeing a couple of wrong answers. It is between A and B. I can tell that people have narrowed it down. We've ruled out D because it says red, one colour. Red was just my example. I forgot about that. Beam of coloured light. It's either going to be bent up or bent down. But when you have light entering a different medium, you must always construct for your ray diagram a normal at 90 degrees to the surface. So there's my normal, my green dotted line. Okay, so my imaginary line to help me with my rules of refraction and reflection. And think about where that ray would go. If it wasn't changing direction, it would go horizontally, like my laser pointer's going. But because it's going to slow down, using all our theories on refraction, that light will bend towards the normal. So well done if you said B from the very beginning. B is the correct answer. Well done. So we're just talking in the chat. I'm not addressing any particular answer right now, but you're sending it to hosts and panelists. So thank you very much if you said B. Well done. And well done to everyone participating. Loads of good participation there. We'll open up the chat to everyone when we're on the longer questions. Okay.
Right. Rachel, just before you move on, I'm in the process of typing up an answer, but I thought people might find it interesting if you shared as well, which is somebody said, does it matter if the coloured beam is strictly one colour or a bit more mixed? And I'm going to finish typing up my answer to the person who's asked, but I thought it might be a good one to point out here as well.
Oh, thank you so much for drawing my attention to that, Kat. Fantastic. So I think the fact that the beam says coloured light, it probably strictly means one colour, because otherwise, well, it doesn't have to, but if it was white light, that would be made up of the full spectrum and all the colours in, all the a full spectrum of colour, Roy G. Biv, if you know that way of remembering it, of visible light. And so we kind of are making a bit of an assumption from the question. But either way, even if it was a colour that's made from mixing two colours, for example, I never can quite remember my colour wheel for coloured light, but still all electromagnetic waves, not just visible light, all electromagnetic waves will slow down when they enter a denser medium. And because they slow down, they'll also bend towards the normal. They'll all refract, is what I'm trying to say. So even if we had a different color, even if we had white light, all of them would slow down and bend towards the normal. But the key with, as someone referenced, famous album cover, and white light entering the prism, is they would all refract by different amounts, because the different colors of the visible light in the electromagnetic spectrum would be slowed down by different amounts. They all have different refractive indices in slightly different in glass. So they're all slowed down slightly different amounts. We don't have to go into all the thorough explanation of why right now, but they would all in general bend towards normal, but by different amounts. And then when they leave again, that's why we start to see the dispersion effect. It's called dispersion. We would have again a different amount of a different amount of refraction for each color, and that causes the spreading of that white light into a spectrum that we can visibly see, and how rainbows are formed through rain droplets. So a nice thing, even if it's two colors, both colors in a beam would refract towards the normal in this example. So hopefully that's addressed. Thank you. So have a little read here. A good first step here is to draw out the important information and then actually draw a ray diagram. So we won't really take answers for this one. This is just sort of setting up the question. I'll show you what I think the important bits of the question are. So it's really important that the refracted and partially reflected beams happen to form a right angle. Find an expression for the refractive index of the medium. So hopefully you've drawn your diagram now, or are just finishing off, and then label everything you're told in the question. So my diagram, and you can check yours as well, check you've labelled as much as you can. I haven't put arrows on it. Oops, sorry about that. But I have my incident ray, where my laser pointer is, my refracted ray, done my best to show a bit of refraction going on there, and then my partially reflected ray. And people often forget about this. At most translucent or transparent boundaries, there will be refraction, which we often talk about, but there might be some reflection. So some of that electromagnetic wave will be reflected as well. And in this question, it specifically tells you. So drawing out my diagram, I'm going to know from that the law of reflection must be obeyed. So my angle of incidence, the angle between my incident ray and my reflected ray, sorry, the angle between my incident ray and my normal is theta, so my angle of reflection must be theta as well. And then the angle between my reflected ray and my refracted ray is 90 degrees, so all drawn on here. And yeah, Kat, it would be great to put the general chat on now, because we're on to longer questions. This is an expression, this question is about an expression for a refractive index of a medium. Please remember, if you've got questions, put them in the Q&A, so me and Kat can capture them.
That's all done now, Rachel, as well. So everyone, you can now talk to each other, share things a bit more widely, or if you prefer, you can talk just to me and Rachel.
Okay. And remember, if you've got questions, pop them in the Q&A, because that's the only place we will answer them. Okay, so we've got our incident ray, we've got our refracted ray, where my laser pointer is now. And then I've also labelled here my angle of refraction between my refracted ray and my normal. And I can use some simple geometry rules, like I've got here. I've got angles along a straight line, which show us that the angle of refraction plus theta must be equivalent to 90 degrees, because all these three angles, theta r, 90 degrees plus theta, must be 180. So angles along a straight line, those two added together must be equal to 90 degrees. So I've got an expression now for my angle of refraction. And then remember what Snell's law is. So that is an equation you'll need to learn. I can see lots of people giving answers. Great work. Okay. And people agreeing, but I've got my incident ray, my refracted ray labelled, forgot I labelled them. I've just talked it all through. My law of reflection, I'm using the idea also.
I think we've just lost you a little bit there, Rachel. I'll come back on camera while we get Rachel back through. So a few questions that people have been asking. People are asking about refraction from different optical densities, one to the other. And it's a case of looking, so refraction will take place, whether you're going from less dense to more dense, but the angle will be different depending on which one you are doing. Hopefully we'll have Rachel back just so we can get her to finish her explanation at exactly where she was. So we'll give her a minute, mostly because I don't have the PowerPoint exactly where she was. We've got lots of questions coming through. I've also posted, for anyone who was interested, Rachel mentioned earlier that the PAT syllabus is on our website, and it's really important for you guys to have a look at the PAT syllabus. And I've shared that as well. So this is our PAT syllabus. And if you follow that through, you'll get an idea of exactly the kind of waves and optics that we are expecting you to know. And included in that is refraction, refractive index, Snell's law, properties of prisms and optical fibers, including total internal reflection. So hopefully you get a feeling for how this tutorial fits in with our syllabus. Should be useful to you. And bear in mind, as we get asked fairly often, there is no formula sheet included. So if you are used to working with formula sheet, just for familiarity, bit of comfort, you will need to make sure you have fully learned all of these equations to use too. I'm really enjoying seeing all the answers you guys are sending through as well. Lots of variations on how you guys are working through the trigonometry, which is lovely to see. And a few of you saying yes straight away. Tried to take shortcuts, got a little bit wrong. Hey, Rachel.
Hi, I'm not sure what happened. I'm
No,
back.
don't worry. Perfect timing. It gave us a chance. We had a look back at what is on the PAT syllabus for this so that people could see that direct relation, how this is a big chunk of the waves and optics syllabus.
Brilliant. Thank you so much, Kat.
No, perfect. And everyone's just been having a little chat. Someone just asked again for the PAT syllabus. I have literally just shared it, so just scroll back up in the chat a few bits. Rachel has started sharing again. She'll give you her explanation.
Brilliant. Okay. And so we're jumping straight into using a sine rule, and I saw a lot of correct answers coming through in the chat, so I'll go a bit quicker. I'm sure you've probably finished it by now. And in the end, we can derive that the refractive index of the medium, so I'm using here the sine rule, for sine of 90 minus theta is equivalent to cos theta, and then substituting in, having made this n, the refractive index of the material, the subject, sine theta, my angle of incidence, over sine theta r, my angle of refraction, is equivalent to sine theta over sine 90 minus theta, because of what I did over here. And that's equivalent to sine over cos, which is equivalent to tan theta. So well done. I saw that coming in very rapidly in the chat earlier. Fantastic. And this is the kind of thing to keep practicing those problem-solving questions, because it's the kind of thing people love to neglect. So here's a much longer question. So have a little look. You're welcome to take a photo. I'm going to send Kat my slides again, just in case. Have a good read. And I've immediately highlighted the two definitions that are the first part of this question. Having the definitions helps you solve the question. Fantastic, and great clarification from Kat. Remember, you don't have to send your answers to everyone. If you just want me and Kat to see them, absolutely fine as well, because I get to see everything in one long list. Can't necessarily address everyone's answers because it gets a bit hectic, but if you've got a question, it must go in the Q&A so we can catch it, okay? So, with this question here, sorry, just moving some things around the screen here. We've got to make sure we're happy with our definitions first of all. So hopefully you're not leaving that to the last step. Write your definitions down now, please. Can you explain what is meant by the phrases total internal reflection and critical angle? So it's not just about problem solving. You've got to know your definitions to start with. So write them down in about 30 seconds or so. And critical angle, you can't just give me an equation. Okay, in about 10 seconds, I'll show you the definitions. Great, it's got some good definitions coming through. You maybe just writing them down on your piece of paper or your whiteboard, that's fine. Okay, so total internal reflection, complete reflection of light within medium. It occurs if angles are greater than the critical angle. And just as a side note, it can only occur when a light ray passes from a more dense medium to a less dense material or medium. Okay, so the green part is not part of the definition, but that's what's important to remember today. And we're going from more dense to less dense. And critical angle, the minimum angle of incidence at which rays undergo total internal reflection. So it's the minimum angle of incidence at which rays undergo total internal reflection. And if I were to draw it as a diagram, which is going to be important because we'll need to draw a new diagram later, I'd have my more dense material, my less dense material, an example of a reflected ray from total internal reflection, but also an example of a ray that is sort of refracting, but when it is incident at the critical angle. Anything greater than that critical angle, so anything where my laser pointer is, the ray will only undergo total internal reflection. Less than the critical angle, the ray will refract when it leaves that medium. A bit like light leaving water. Okay, so we've got this longer question here. The next step of the question is to derive an equation relating critical angle and the refractive indices of the two materials. There's an important factor here where N2 is less than N1. So the refractive index of N2 is less than the refractive index of N1. And that means that N2 is less dense than N1 as well. So we're going to need to use Snell's law to solve this problem. And yes, good. Remember to put questions in the Q&A, but I actually just saw something. You can use these laws. These are equations. These are laws of physics, and you can use them in your problem solving. But that won't be the final answer. That will be one step along the way. So we've got these two materials. Okay, and that's later. Sorry, we're going to firstly be using Snell's law. So we know that we have total internal reflection if the angle of incidence θ1 is greater than the critical angle. So anywhere here we'll have total internal reflection. And we need to derive an equation where N2 is less than N1, which is actually the example here. N2 is less dense, and so the refractive index will be less. N1 is more dense, the refractive index will be greater. Good, I can see lots of correct answers. We're going to use Snell's law, but hopefully you've done this in your studies, your current studies, because at the critical angle, the angle of refraction would be 90 degrees. So where I've drawn this red right angle, did my best there. Okay, so that will be an angle of refraction of 90 degrees, and you can probably see where this is going. And that would be at the critical angle. Theta, the angle of incidence, θ1 is the critical angle. And you're correct, loads of people have said this, well done. Sine of the critical angle is N2 over N1, that ratio. So that's what that question was actually asking. If we just go back a step to the question, sometimes it's about understanding what the question is asking. Derive the equation relating the critical angle and the refractive indices of the two materials. So the minute we see that point critical angle, Snell's law will always apply during refraction, even if it's refraction at the critical angle. So we're just practicing our physics here. So actually, you really only need to learn Snell's law. This bit you should always be able to derive, okay, as a physicist. Next, we're looking at the longer part of the question. We've got information about the optical fibre. You'll have learned about the core and the cladding. Okay, and the core is where that total internal reflection is going to happen, but it only happens because of the cladding. Lots of people don't remember that. So have a good read of the last section of the question. And I would first recommend redrawing the ray diagram for light entering the core from air at the maximum angle. So redraw this point here for your problem solving. And then redrawing it where it first hits the cladding. So That's where we're going to be really interested. The only way it will be able to reach the other end is through total internal reflection. So the only thing we can know is the critical angle. So we can make an assumption to start this problem solving that we are going to have an angle of incidence at this core cladding boundary that is at the critical angle. So I'll show you a few next steps. Optical fibers always actually contain a core and a cladding where the refractive index of the core is greater than the cladding. And this is what allows total internal reflection. So here's my redrawn diagram. So of that left-hand side, actually I'll give you a little bit more time if you're redrawing that section of the diagram.
Just while Rachel's giving you that extra moment, I'll just address a question I've had in the chat, Rachel, which was, is this still relevant when we're doing multiple choice? So I just wanted to say to everyone, absolutely. But what you might be looking at is just a different way of the question being phrased. So it might be which of these expressions could represent an equation that could be derived. So all the same skills, but you then select your answer at the end.
Exactly. Thanks very much, Kat, because it's still the correct physics is going to lead to an answer. And it's about being able to do the process and to be sure you're choosing that correct answer or steps along the way. Okay, so moving on to my diagram. So for me to problem solving this question, I'll be drawing this by hand. But I'm just really interested in that first bit. And there's multiple routes to solve this question. I'm going to show you one of them. Redraw the ray diagram for the light entering the core from air at the maximum angle of incidence. And we can show refraction as it enters the core and then as it hits the cladding, the refraction along the cladding. So at the very least, at the critical angle, we'll have this refraction. I know we might be thinking about total internal reflection eventually, but at the very least, if this ray travels all the way along the cladding, it will reach the other end of the optical fibre. And that's what we can know for sure. We've also got some information about angles. So I know if I turn this into a triangle, I know that I've got the critical angle. I know that I've got this mystery angle here, which I can derive as 90 minus the critical angle, because I know that this side corner of the triangle is 90. So I've already mentioned that. We're going to assume transmission. I think this is the bit that people get confused about. We're going to assume transmission at maximum incident angle when the ray meets the core cladding at the critical angle, because that ray will get to the other end of the optical fibre. So at A, we know that the critical angle equation we just derived is going to be relevant. And at B, because we have refraction only in this ray diagram, we will have Snell's law relevant. So we're going to need to use that. So let's address that first. At B, we're going from air into the core. So the refractive index of air is 1 again. I've got my maximum critical angle, that is what I'm trying to derive. Always remember the purpose of the question. And I've got my refractive index of the core, due to sine 90 minus the critical angle. So that seems familiar. We've got that sine of 90 minus the critical angle from the triangle, where all the angles add up to 180 degrees. Good, I think some people are checking with each other. Fantastic. It's hard to keep up with formulas when they're typed in the chat. And remember again that sine of 90 minus theta is equal to cosine theta. So that's going to be really useful in this question. And if you just want to try something, you try that substitution. If you've taken a wrong step, you can just go back. Okay, so that shows us that sine theta max is equal to n core cos theta c. And that's equivalent to n core square root of 1 minus sine theta c squared, because sine is going to be more useful. And you might not realize that at first. So we can go and use that in a second. That substitution comes from these trig equations. Okay, I know that sine squared x plus cos squared x equals 1. And you'll see why I've used that in a second, because using equation A, my critical angle equation, okay, So some people are frustrated they can't find a way to simplify it more. Let's see how simple I get it. Oh, I didn't realize we were going to show up in one go. Okay, so we're going to substitute in to the equation. Sine of the critical angle equals n cloud over n core, because we've derived that earlier. Substitute it into this equation that we've derived using Snell's law and all these trig rules. Okay, so when I substitute that in, there are a lot of neatening up, well, a lot, but not completely. Not sure how happy you'll be with this. Okay, so we've substituted that in here. We can actually simplify it slightly to get that to this point. And then this is as simple as we can make that derivation. So the equation for the maximum angle of incidence is arcsine square root of n squared core minus n squared clad. Okay, and remember that you will be given options that are different and different simplifications, so you'll need to be able to get to in a problem-solving approach. So always practice simplifying your equation. And if you think it's messy trig right now, make sure you have another go at neatening it up. Can you get to what I've got here? Okay, and double check you're working. Great. I'm just going to go back to the question because I've seen a question in the Q&A. Okay. So I had a question in the Q&A. About how do we know total internal reflection doesn't occur at the initial boundary between air and the core? So that's this part here. And I suppose it's because there are a few assumptions we're making, but I suppose it's because the purpose of an optical fiber is to transmit the electromagnetic radiation. And the start of this bottom part of the question does say light may only be transmitted along the fiber if the incident angle, it leads us into the idea that there will be transmission. So, well, actually, I've got another reason as well in a second. So firstly, it's got to refract as it enters into the glass clad, the core. The other reason is cladding core. What's another way to explain it? The only reason we've got the total internal reflection in the core compared to the cladding is the refractive index of the core is higher than the cladding, so it's more dense than the cladding. Air is less dense than the core, so you also couldn't have total internal reflection there. But it's a good question. It's about checking where the question is leading. It's giving you a condition. It can only be transmitted along the optical fiber if, and then it explains that context. So good question. The last two lines of working, there are a few steps missing from here, where I'm highlighting right now, to here. If you work it through, you will be able to get from, notice we've got n core on the outside of this square root. So if you square everything that's in this bracket, and then if you put square root of n core squared on the outside, as it were, you will be able to simplify to this point. Okay, if you keep working it through, and then the last step's the easier one. Where that came from, if you're asking about that question, is the substitution of sine of the critical angle into this equation here, which came from Snell's law at point B. So I try to always say where I'm doing my mathematics, I'm at point B between the air and the core, and then we're using the equation about refraction along the critical angle. Okay, and we're making the assumption that for transmission, the ray is traveling along the critical angle. So just for Ali in the Q&A, about the incident angle have to be greater than the critical angle for total internal reflection, we're actually assuming that that ray will hit the boundary between the core and the cladding at the critical angle, which is what this diagram is showing. So hitting the boundary between the core and the cladding at the critical angle. for all the light to be transmitted. We couldn't really solve it if we were doing lots and lots of total internal reflection. That we would not be able to get, I don't think we would be able to get to a solution in this question. And if we would, it would take us a long time, okay? So that's the problem-solving approach. How can we simplify and make an assumption that that's how we'll get maximum transmission? Okay, so I'll move on for now to the next question, which again is a lovely optical fibers question. Have a good read. I'll just grab a drink of water. Any questions, remember, in the Q&A. Again, a diagram. Okay, so just had a good question about a single plane. I guess the most straightforward way to think about it in this question, well, if you're thinking about three planes, you could think about X, Y, and Z. So X and Y you might think of on an axis of a graph, but we're thinking in 3D, so X, Y, and Z. In this question, when they mention the meridional ray, I never quite get the hang of how to say that, but they're introducing a new idea here. It's one which bounces off the walls of the fibre yet stays in a single plane. So you are being told that it will bounce at least once off the walls of the fibre, but it's staying in that single plane. So it's not going to be moving off in like the Z plane in another dimension. We can model this more straightforward. Then we're making a few assumptions about how it's being transmitted along the fibre in terms of that plane. It's probably the best way to think about it. And there's quite a lot of information in this question, and there's no diagram. So even if there's a ray diagram, always redraw it on your whiteboard. But here you're going to need to construct one to help yourself solve it. And also it's the idea that that ray is going to pass through the axis of the optical fibre. So it's going to be passing through the sort of central path of the optical fibre. We've got information about the core, the cladding. And for the first part of the question, so we're just going to focus on part A at first. We are going to need to use refractive indices to calculate the critical angle for that optical fibre. Can you make a straightforward assumption that's going to help you solve it? Because otherwise, as some of you are probably thinking, how do you start with that question? Okay. At least the best way to think about square pulses of light are a digital signal. Okay, so either sending a signal or not sending a signal. Okay, so an assumption you can make is that the maximum path length is when the ray hits the cladding at the critical angle. So just like the last question with that optical fibre, if you know we're dealing with an optical fibre, you might be able to make an assumption to do with using critical angles. We've got the minimum angle a ray can bounce at is controlled by the critical angle. The question even hints that. So let's draw a diagram of how we know that that ray can be transmitted, which again, just like in the last question, is if that ray hits the core cladding boundary at the critical angle. So actually very similar part of the question, part of the problem solving. Okay. Meg, well done. Fantastic. So we've got information about the two refractive indices. Always lay out your working for your problem solving. And the assumption that we can make, as I've said a few times, is that the maximum path length occurs if the ray hits the cladding at the critical angle. So we're going to be using that critical angle rule again. And we can use that to actually find the critical angle if we need to. And the assumption that we can also make is maybe that could be happening at any point in the fibre, but we could assume that it actually won't hit. Actually, this is where the sort of single plane comes in, apologies. It actually won't hit until the end of the fibre. So I saw someone mention in the chat about why don't we treat it as a triangle? Yep, that's going to be really helpful in this question. So it doesn't say where it's going to bounce along the fibre, but it could hit the optical fibre quite near the end of the optical fibre. So actually, light can travel, where my laser pointer is there now, 1 kilometre straight down the middle of the fibre. That is totally possible. It can happen. But we're also looking at this meridional ray, and we're making an assumption that it will hit the optical fibre near the other end of it, and that will be the extra length that it is going to travel. The critical angle we've just calculated using the two refractive indices, and I've seen a lot of correct answers come in, so well done. You'll see the big reveal in a moment. But yeah, modelling it as a triangle was the route to take here. We didn't say where it hits the boundary between the core and the cladding, but we're making an assumption that it will hit near the end. And it does give us that information about the single plane. So well done if you said that the maximum path length would be 1.00267 kilometers. Oops, sorry, moved on too soon. And as that is the correct answer. So well done. Okay, fantastic. So we are making a few assumptions in that problem solving, and never round too early. So always store your significant figures in the calculator just in case you need them later. Okay, I'll go back to part B of the question. If anyone's got any questions or wants me to go back, just say that in the Q&A. But then there is a next step, which is to calculate the time difference for this ray and a ray which passes straight through. And then if square pulses of light are used, and I'll show you a picture to represent that in a moment, calculate the maximum rate at which information can be sent. So we've got a path difference by modelling the path that the light could take straight down the middle at 1 kilometre in distance. We found the maximum path length. So we know how much longer the maximum path length is. That's the total maximum length. And we're going to now turn that into a time difference. So in order to calculate a time difference, my students always get a bit confused about this, but path difference and time difference are different things. Path difference, especially if you do know the length of something, is a distance. So path difference is a distance. We knew that we had a 1 kilometre distance, and then we had that new value. So our difference in path length is 2.67 meters. But the thing that links time and distance will be speed. We're dealing with electromagnetic waves. Okay, so we've got to go with that known quantity that you use and take for granted probably all the time, the speed of light. So the time difference can be found by using the path difference divided by the speed of light. But we are not dealing with a vacuum. We are dealing with a core and a cladding. We're actually dealing with the core, sorry, not the cladding right now. We're just dealing with the core of the optical fibre. So think about what other equations do you know from A-levels or your studies of how to relate then refractive index and speed. Okay, good. I can see lots of attempts coming in. They seem familiar, so I think we're on the right idea. So another equation to learn is that refractive index and speed are related by the equation that refractive index is the speed of light divided by the speed of the electromagnetic radiation in the material. Because that's really what refractive index is, just a ratio of how the speed changes. Okay, it takes my students quite a while to understand that. This is just an index, a bit like density is a material property. Different materials will have different refractive indices by how much they slow down or speed up, slow down, to be honest, the speed of that electromagnetic radiation. If I change the subject, the refractive index of the material will be the speed of light in a vacuum, speed of electromagnetic radiation in a vacuum, divided by the refractive index of the material. And I know for the core, it's 1.5. So I can see quite a few people getting that. So you're right, the time difference is 1.335 times 10 to the minus 8 seconds. So that's from using the path difference, 2.67 meters, divided by 3 times 10 to the 8 over 1.5, as you can see in the working. And then the final part of the question is if square pulses of light were used, okay, good, so it is about 13 nanoseconds for people saying that, fantastic. We're now going to try and turn that into a rate. So whenever you see the word rate in any problem solving question, you always need to think about, okay, that's something per second or per unit of time. So square pulses, the shape might look like this. And this is an example of a digital signal where signals are sent with ones and zeros, something we used to teach about a lot more on some of the old specifications. So signals sent as ones and zeros, and this is kind of how life works with optical fibers. We're not just thinking about the ray passing down, but how we're communicating and sending signals with those optical fibers. But we actually need to assume, because the path difference and therefore the time difference between these two most extreme versions of the rays was given by our time difference for those rays to travel, which is very, very small. There's that amount of time between pulses, and we don't want to overlap the digital signal, otherwise we'll get interference in our signal and the signal won't be clear. Okay, we won't send a clear message with that optical fiber. So for no overlap, we need that time difference between each signal. We need that gap of 1.335 times 10 to the minus 8 seconds between each of those pulses, because a 0 is no pulse being sent and a 1 is information being sent. The gap must be this. So regardless of the peak length, the gaps need to be that many seconds. So that means that we can only send a maximum number of about 75 million per second, because to turn that time difference into a rate, the number per second is 1 over the time difference, which gives us 7.49 times 10 to the 7 per second, which is 75 million per second. And I think if you, there's a bit of clarification from someone else in the chat. Yeah, using the wrong speed of light. Remember in the core, we do, maybe if I go back one slide, we do have to remember that in the core, although that seems like such a simple equation here, that the time difference is the path difference over the speed of light, we have to remember that that speed of light will not be for a vacuum, it'll be for the core. So we have to use the refractive index of the core being the speed of light in a vacuum over the speed of light in the material, and then change the subject, put in the refractive index of the core that we know, and in this equation, use that new ratio for the speed of the light in the core, and that will give us the appropriate time difference. Okay. The time difference is the minimum. The time difference is the minimum gap, because we're sending that signal And we don't want this bit of the signal, the one, and this bit of the signal, the other one, to be muddled up. We can't get two bits of signal overlapping, otherwise there'll be interference and unclear signals. They might be actually much longer than that. I've drawn them very uniform. But we're just thinking of how we're going to send those bits so they don't overlap. There has to be a gap, and that gap can be caused by sending the signals on different paths down the optical fiber. We don't want interference. And so the minimum gap we need is for this ray to have reached the other end. Sorry, this ray to have reached the other end just before maybe one that's gone along the meridional route and taken that a little bit longer. So that's why the gap has to be that time difference. So hopefully that helps a bit there. And this is an assumption we're making to help us problem solve this. And another really good question about what are we transmitting per second? Yeah, pieces of information. That's what's coming through the optical fibers in some ways. We have systems that decode that information, but we're kind of sending a series of ones and zeros, just using electromagnetic radiation without going into too much more detail. But yeah, sending information. Okay. So hopefully that's answered those questions for now. We still might send more than, it might be a series of ones and zeros, and we might have longer gaps. So we've had a question about if the length of the peaks is longer. So I probably should have made that clear. There will be a bit of a gap between each signal that's a one, but you might send multiple ones in a row and then lots of zeros. And we also have to work with the information we've got. So how can we, what's the maximum rate? You're right, there might need to be a lower rate than that. So if the peaks are longer or there's more ones, then we might need to lower the rate that we send information at, but the question was about the maximum rate. So that's why that information covered it. Okay, so I'll pop the next question up and you can have a little browse of this. This one probably will need some redrawing. My number one tip is draw your own ray diagram. Okay, so hopefully you've had a little read through. I'll just do a bit of highlighting. We've got mirrors here, so no more optical fibers for a bit, okay? And we have the terminology 2 alpha, and that is drawn as two separate alphas here. So that's my angle 2 alpha between them. We have faint parallel beam of light consisting of rays parallel to the central axis, shown by the single ray A, where A is equal to alpha. So that's really important. That last sentence there is going to help us a lot. And then the first part of the question, there will be some more, is determine the rest of the lettered angles in terms of alpha. So draw your own ray diagram to solve this. I've added on a bit more information that I know. And we're going to be using some laws of reflection. So actually, hopefully quite quickly, you can type in the chat bar what B is straight away. Excellent, well done. And remember, all answers will need to be in terms of alpha. And when you've got an answer for C or D, or E can keep going. So we're going to use a lot of geometry rules here. So you're right, B is alpha. We can do that very quickly using the law of reflection. C and D are also to do with reflection, but they're unknown. And you can clearly see from the image that they are not the same as A and B, but they are as yet unknown. And we're going to need to use rules for angles along a straight line, adding up to 180 degrees. And also remember that you can see a few sort of triangle shapes here, angles in a triangle adding up to 180 degrees. What you'll end up with in the end is 2 or 3 simultaneous equations. So my tip is look for what you can eliminate and then solve for C, D, and E. Also, it can help to redraw sections of this at a time and maybe draw more than one part of it so you're not just working on one diagram the whole time. So well done, I can see some answers coming in. We should not have, just to clarify, I'm just checking my notes, we shouldn't have 90 degrees in any of the final answers. They should all just be factors of alpha. Okay, so well done. I can see some people, the penny is dropping. I can see some good attempts. If you give an answer, write the whole answer together maybe, so I can have a quick check. Okay. But I've labeled that B is alpha and I've just redrawn one part of the triangle. Okay. I might deal with the fact that angles along a straight line add up to 180 degrees. So this angle here that I've labeled, my green angle, will be 180 degrees minus E minus alpha. And that is because, oh, sorry, that's not angles of a straight line. Got confused about which geometry rule I meant. In the triangle, all those angles will add up to 180 degrees. So this mystery angle here is 180 degrees minus E minus alpha. There's probably multiple ways. You might not have done it the same way. But then also along that straight line, C plus D plus this green bit here will all add up to 180 degrees. So my first equation that might come in handy, but not my final answer, is equation 1 here. So then, okay, I'm going to draw the other part of the triangle, the other triangle I can see. So I'm just separating them and drawing each section one at a time. And in this triangle, 2 alpha plus D plus 180 degrees minus E, because of angles along a straight line, are equal to 180 degrees. And we can simplify that a bit more to 2 alpha plus D is equal to E. So you can check that that works. I've got the angles in the triangle on the left-hand side, all adding up to 180 degrees. This one here comes from angles along a straight line. Okay. And I'll check a few things coming in the chat bar, see what you can do next. So well done, Josephine. Basil, just check E again. Stephen, check E, but I think you've got C and D correct. Well done. Can't check everyone's, but I'm doing my best. Yeah, well done, Theo. That's great. Oh, my computer's been very slow. Hold on a second. So hopefully you're having a go, or maybe you've done a slightly different route, but I'm going to try substituting equation 2 into equation 3 because I have a term for E there, and I can just pop that in to equation 1. So I've substituted in clearly because I'm trying to color code a little bit. And then I'll end up with C being equal to 3 alpha. So obviously those D's cancel, and I'll get a nice little term for C. So C is equal to 3 alpha. And then I know that C and D, because I've essentially got reflection and I've got a straight line down here that those two rays are reflecting off, C and D are actually the same thing. So loads of you are getting that answer. Fantastic. D is equal to 3 alpha. Elliot, well done. Basil, good correction. Well done. And then if I know that D is equal to 3 alpha, I can just pop that into equation 2. As long as I'm laying my own working out clearly on my whiteboard or my sheet of paper while I'm practicing. And I can prove that E is equal to 5 alpha. So quite a good little problem solving to take a method to take it one step at a time. We don't want to end up with any angles in degrees anywhere, but we do use them along the way. Yeah, well done. Good clarifications. Well done. People sending in answers. Okay. So there is a part B to the question, but the big tip here is don't forget to use simple geometry rules, like angles along a straight line or angles in a triangle, all adding up to 180 degrees. So if you're not sure where to start, look for the shapes that you can recognize. And also we were using simple reflection rules like here. Okay, part B gives an explanation. Think about what will happen after several reflections of light down the mirror funnel. Have a think about what happens, and if you want to write that in the chat bar, you can. I'll go through that in about 30 seconds. And then in part C, we're given an if. So if angle alpha is 10 degrees, what is the total number of reflections that will be made by a beam of light entering parallel to the axis of symmetry as shown? And because it says several reflections, it just means if you kept on letting the reflections happen, what will happen eventually? So just to clarify what someone's just put as the answer. Yes, the angle reflection will change. That will actually help you with part C. But for part B, think about what will happen eventually, especially if you've ever learned anything about bike reflectors. That was what we always traditionally did as our example. Yeah, Gabriel, well done. Because it's a mirror, we actually don't worry about any energy being absorbed, Alice, but it's a great way to think about things. We assume 100% reflection unless otherwise stated. You do have to think about that a little bit with refraction sometimes, partial reflection, refraction, but well done. Yeah. Jamie, well done. Okay, about 10 seconds, I'll go through part B. And part B will help us with part C. Well done, Sophie. Might give a bit longer, got some good ideas coming through. Milian, that was a good idea, saying about will the rays start to interfere with each other? But remember, this is a ray diagram showing where the path has travelled. Probably best still to think about this as one beam of light being sent and the path it takes. So we're not actually worrying about interference in this question. But I like your thinking. Well done, Stephen. Okay, and then even when, a few people said the angle of incidence will be 0, or they've said it will reflect at 90 degrees to the mirror. Okay, but then what will happen next? Just gonna challenge you there. So well done, you're right, that the angle of incidence will eventually be 0. And Theo, you've got it, and that's in the chat for everyone. But yeah, eventually the ray will come back out again. So eventually, it probably helps that I drew on that ray here, but well done, some really good logic. And I like the way everyone was thinking there. But eventually, and this is not an exact diagram, I've just added that purple ray on. I could have added it anywhere along here. But eventually, you will get a ray that is likely at some point, even if it keeps reflecting all the way to where my laser pointer is, to reflect at 90 degrees to the mirror. And the minute that happens, the beam will travel where my orange beam is. And it wouldn't even necessarily happen exactly here, but I'll just draw the diagram. And along where the orange beam is there, and then along there, and then along there, and then back out. So it's not necessarily exactly like that. But you're right, eventually it will just come back out of the funnel. And if you look into bike reflectors, and that's why if you're got headlights on the car, you're behind someone on a bike, even if just as, bit of a grey day or something, you should see the headlights reflected off their reflectors because of the structure, not because they're mirrors, but because of the structure of that material. Okay, so for part C, we need to use our answer to part A. Okay, so we have our value, not values, but our terms in terms of alpha. Okay, and remember, we're not talking about the critical angle in this question because we're dealing with the mirror. So remember, you've got a question put in the Q&A, but I did happen to see that one. So we're dealing with a mirror here, and we're talking just about reflection now. So for part C, if angle alpha is 10 degrees, we're given that value originally, so we can actually know what all of these angles will be for A, B, C, D, and E. So in part C, we know that A is 10 degrees, that's the first reflection. Yes, B is 10 degrees, but that's not a separate reflection, that's involved in that reflection there. So C is 30 degrees, E is 50 degrees. There'll then be another reflection at 70 degrees because I've got a bit of a pattern going on. Okay, I can spot what the pattern is. And then, just like we've talked about to solve part B, I'll have that angle of incidence that is 90 degrees to the surface of the mirror. Okay, so we've spotted the pattern, and that's one reflection, and then it will go back on the same path. So the next one will be 70 degrees, the next one will be 50 degrees, the next one will be 30 degrees, the next one will be 10 degrees. So well done, loads of people saying 9. Just be really careful with this one. It's not 10 because we can only have one ray being reflected at 90 degrees, and then we go straight back to the 70 degrees. So that's why I've written such a weird sum, which is 4 plus 1 plus 4. 4 reflections on the way in, 1 reflection at 90 degrees, 4 reflections on the way out. So we have 9 points of reflection. So quite a fun little question there. Probably you don't have time for that one, but in the problem solving pack, there is part E, D and E. So you can think about that question in a little bit more detail if you wish. But I think I'll leave it there and wish you the best of luck. Oh, there's a lot more stuff there than I thought. Oh yeah, there you go. Good luck with your summer practice and also with the rest of your studies. And thanks very much. Any questions, might have time to answer them now in the Q&A. But just remember, work through the syllabus, practice every aspect of your physics and maths.
Thank you so much, Rachel. I have to, waves and optics is one of my favorite bits of physics, so I always really enjoyed this session.
Brilliant.
And let's give everyone a second, see if any questions specifically about Rachel's work today come through on the Q&A. A few people have asked to go back through solutions, and don't forget, I'm going to be sharing the recording tomorrow morning. So anyone who feels the need to go back through, you can absolutely go back through the recording. People are asking about the sample paper. Just go back to those main links that I share in every single email. So the main university link will now take you to the sample paper. And for those of you asking about how you can practice more, tomorrow morning, I'm going to send everybody an email. It will contain this recording, so you can watch it again if you find today a bit tricky. It will contain links to the practice paper, so you can have a go at that. And it will contain a problem set that you can work on for next week, all looking at waves and optics. And next week, we'll be joined by 2 of our current students who will take you through the solutions to those problems. So that will get you having a look at the Q&A now, Rachel. That will get us through practicing more, where the sample paper is, recommending more questions. So I think we've got those. There's a particular question about why the light doesn't leave until 90 degrees, because it's greater than the critical angle, which I think just takes you back to the fact that it's a mirror, Rachel. And I think if you can do that in about 60 seconds, we'll be able to cover that one as well.
Sorry, I forgot to unmute.
No, all good.
Yeah, I think that final question, when we're dealing with mirrors, we're not thinking about the critical angle because that's when we're dealing with refraction or light traveling in a medium. Remember, with a mirror, we're just hitting a different medium and dealing with reflection. And the light reflects along the same path because of the geometry of the situation, I suppose, in some ways. But the only way for it to if you've got one point where, especially that you're looking at this diagram, this was just a sketch, but when you eventually have one ray that hits the mirror at 90 degrees to the normal, it's a bit like staring your eyes directly in front of you in the mirror. You are seeing the light is traveling to oh, that's a bit more complicated than that, but back towards you from the mirror, and that's what's happening there. And it can only travel back to where it came from. So then you're traveling back along exactly the same path. So if you've got an extra question on top of that, let me know. But hopefully the diagram on the screen helps you with that.
Fantastic, thank you. In that case, I think we are going to round up for this evening. Rachel, thank you so much for your input. Thank you to everyone who came today. I hope you find it really useful. And I will be in touch first thing tomorrow morning with all of those links and the recording. And obviously, we'll see you again next week for PAT webinar number 4. Thank you very much, everyone.